So, in the mechanism, if you look at the first step is basically the concerted addition reaction. So, this is one of the reason we can say either the mercuration oxymercuration reaction or demercuration reaction or the hydroboration oxidation reaction, we do not have a carbocation which is formed. In other words, these reactions does not undergo rearrangement, because in this hydroboration reaction, this is a concerted addition. That means, boron adds across the double bond in a single step. So, here is an example. There are two carbons. This is a more substituted carbon, this is a less substituted carbon, because here we have a hydrogen atom. So, how the boron can add? So, boron can add like this, the boron can add to the more substituted carbon, that is one way of addition. Boron can add to the less substituted carbon, that is also another way. So, there are two types of addition possible. So, between boron and hydrogen, hydrogen is more electronegative. So, we need to exactly find out whether the hydrogen will add to which carbon. We can actually decide very easily, because the electronegativity difference actually can help us identify how the addition will take place. So, boron, if you look at the borane reagent, especially BH3, the atom boron is more electropositive, that is what we have seen. Hydrogen is more electronegative than boron. So, the boron is a electrophile which is going to add to the double bond. So, as we have seen earlier also, how the addition generally takes place in the electrophilic addition, the boron attaches itself to the less crowded carbon atom or the terminal carbon atom. So, that is the reason the boron having a delta plus charge adds to the less substituted carbon atom. Now, the question will come, why boron adds to the less substituted carbon atom? Because if you look at the charge, this is not a negative charge compared to this particular carbon. When we look at two carbon atoms which can have or stabilize a negative charge better, if we look at the less substituted carbon atoms are more prone to stabilize the carbon having a little bit negative charge, especially in the case of double bonds. So, in other words, a carbon with one methyl group can stabilize this particular negative charge. In other words, the electron density on this carbon is going to be high. So, the boron which is electropositive or the electrophile can easily attach itself to the carbon which is having comparatively more negative charge. So, that is the reason boron and carbon forms weak bond, and hydrogen actually attaches itself to the more substituted carbon atom, because this is more electronegative. In other words, this is the nucleophilic end of this BH bond. So, the electrophilic end adds to the less substituted carbon, and the hydrogen adds to the more substituted carbon. So, this is a concerted addition. In other words, hydrogen and boron adds from the same side. If you look at, so this is what is called a syn addition. And finally, what happens is the boron is actually cleaved to get the hydroxide derivative. The removal of boron is actually little bit complicated, or in it is a complex mechanism. So, how the reaction actually proceeds is, the reaction happens in the presence of hydrogen peroxide. So, the hydroperoxide anion, and also we have a hydroxide anion which is used as a base. So, the hydroxide base produces the hydroperoxide anion in the first step. So, this hydroperoxide anion attacks the boron, followed by a concerted intramolecular shift of oxygen from boron to carbon takes place. So, basically when we look at here, the hydroperoxide anion actually attacks this boron, then the oxygen actually shifts from boron to carbon, and this boron now goes and attaches itself to this particular thing, this oxygen. So, there is a internal concerted intramolecular shift takes place, and this leads to oxygen getting attached to the carbon atom, and the final cleavage of the oxygen boron bond, because we have a boron bond, oxygen boron bond is there. So, once it is cleaved, hydrogen adds to this side and OH adds to this side. So, that is the reason we finally end up with the boric acid as our final product. So, if we continue to look at the mechanism, this is a syn addition as we mentioned. That means, this is actually happening with the retention of configuration. Now, the question we will once again ask the question, why boron adds to the terminal or the less substituted carbon atom. So, the reason is, normally in a double bond, as I mentioned, the less substituted carbon can actually stabilize the negative charge better. In other words, this particular carbon can have a negative charge more easily, and boron being an electrophilic end that attaches the electrophilic end attaches itself to the nucleophilic part of the double bond. So, that is the reason boron adds to the terminal carbon atom, and hydride ion adds to the internal carbon atom, and this is actually happening, we call this as a stereoelectronic effect. So, this stereoelectronic effect is one of the reason the reaction is being controlled by this particular syn addition.